Now we should switch to Dario's talk, the next talk, right?
Yes.
And before we start, I saw that there are a couple of newcomers. Let me remind all of you once more, if you have a question during the talk, the best is probably to use the chat. I'll keep an eye on the chat and eventually unmute you. And certainly there's also this question and answer session in the end. Yeah, you can always raise your hand as well. And I'll also check for that. Good. I guess we have 1 minute before, but why don't we just start with Dario now? Dario Frascaria is currently in the OR group in Amsterdam, and he's talking about some joint work with Neil Olver about algorithms for flows over time with scheduling cost. Please go ahead.
Can you hear me now?
Now we can hear you.
So, okay, sorry for that. Thank you, Peter, for the introduction. So the object of this study has been to find the optimal flow over time with scheduling cost. And in this talk, I will first introduce flow over time. Then I will introduce scheduling cost. And then I will talk about the technical part. So in a flow over time setting, we are given a directed graph G, a source S, and a sink. And this setting is continuous. And to each arc are associated two constants, a capacity and a free transit time. The capacity indicates how much flow can enter an arc per instant, and the free transit time indicates how long it takes for a particle to cross the entire arc once inside. So you can think of an arc like a pipe, where the capacity is the width and the free transit time is the length. So here I can show you an example of arc dynamics. And in this example, the arc has capacity 2 and transit time 1. And suppose that for some period of time, we have an inflow of 4, which is bigger than capacity. So what will happen is that a Q will build at the beginning of the arc. And this Q will keep increasing as long as the inflow is bigger than capacity. And only once the inflow drops below the capacity, this Q will start depleting. Moreover, we also have flow conservation constraint. So we have that the flow can be generated only at the source and not in the middle of the network. So we have seen an example of arc dynamics, and now I'm going to show you an example of a flow over time. So I will show you how a flow over time looks like with a sequence of snapshot. In this example, we have that all the capacity are equal to 1, and that the free transit time are equal to 1, except for the free transit time of the arc AB, which is equal to half. In this example, we have that we have an inflow into the network equal to 2 for 1 unit of time. And we have that the flow split evenly between the path SABT and SBT. So what we will see is that the flow will start moving towards the sink. At time 1, we have that the inflow drop to 0. At time 1.5, we have that the inflow into the arc BT is equal to 2, which is bigger than capacity. And so we will see a Q forming. And this Q will keep increasing as long as the inflow is bigger than capacity. Then it will become constant. And only at time 2.5, it will start depleting. So only once the inflow drops below the capacity of the arc. Flow over time have been studied both from the combinatorial optimization community and the game theoretical one. They were introduced by Ford and Fulkerson in the 58. And classical problem in the combinatorial optimization literature are like the maximum flow over time, where we are given an interval and we want to know how much flow can reach the sink within this interval, or the quickest flow, where we are given a total mass and we want to know what is the smallest interval in which this total mass can reach the sink, or the LS-Riva flow, of which I will talk more about later. But we also have settings with multi-sinks and multi-sources. In the last decade, following the work of Koch and Scutella, flow over time have been studied also from a game theoretical perspective, and here they are used to study to model traffic equilibria. So here we have that each flow particle represents an agent that wants to arrive at the sink as soon as possible. And the flow is released into the constant at a constant rate. And this constant rate is given as a part of the input. In the literature, we can find results on the existence uniqueness or on Parseval anarchy, but we also have results on structural properties and multi-sinks and multi-sources settings. So in this work, we use scheduling cost function. So here we have an additional cost. So each particle has an additional cost that depends on the time when this particle arrives at the sink. So the total cost of the particle is given by alpha times its travel time, and this would be the journey cost, plus the scheduling cost that depends when the particle arrives at the sink. So here we can see an example of scheduling cost function. Here the cost for arriving at T star is 0, while the cost for arriving before T star reduces with rate beta, or for arriving later increases with rate gamma. So if one particle arrives 2 units before T star, in this example we'll pay 2 beta, and if he arrives 2 units of time later than T star, it will pay 2 gamma. So the motivation for this scheduling cost setting arises from the morning rush hour. So here everyone wants to arrive at the office at T star, but if they arrive earlier or later, they pay a penalty. And usually the penalty for arriving later at work is bigger than the penalty for arriving earlier. So you can think of T star as like 9 a.m. in the morning. So scheduling costs were first introduced by Vickrey in the 1969, but they soon became the standard in the transportation economic literature because they are used to study equilibria with endogenous departing time. So equilibria where each agent choose its departing time and its route. So that means that in an equilibrium, every agent will have the same cost, but the first agent that arrives at the office will have a small journey cost because it will encounter no queue, but it will have a big scheduling cost because it will arrive way earlier, while the agent that arrives exactly at the star will have no scheduling cost, but it will have a big journey cost since it will encounter a lot of congestion. So in this work, our goal has been to compute the flow over time that minimize the sum of scheduling cost and journey cost of all the agents. So now I start talking about the technical part, and I will talk about the earliest arrival flow. And this is a flow that maximizes the amount of flow arriving at the sink simultaneously for all points in time. Then I will talk about the optimal flow in this setting, so the optimal flow with scheduling cost. And this flow is a generalization of the earliest arrival flow. And then I will talk about Tolsted equilibria, so we'll focus about the game theoretic setting. So the earliest arrival flow algorithm is based on the successive shortest path algorithm for the static mid-cost flow problem. Here we are given a time horizon, and in each iteration we compute the shortest augmenting path in the current residual network, residual graph, and we send flow along this path in the interval 0 t minus tau pi, where tau pi is the length of this path. As here we only do it if t minus tau pi is non-negative. So, okay, here I can show you an example. Now in this graph we have that the first element of a label indicates the capacity, and the second element indicates the free transit time. So at first, the shortest path is the path SABT, and this path has length 3. So we will send 1 unit of time in the time interval 0 t minus 3. We send 1 unit of time because the minimum capacity along this path is as capacity 1 is 1. Then in the residual graph, we will find 2 augmenting paths that has length 4 and residual capacity 1. So then we will send 1 unit of flow along these 2 paths in the interval 0 t minus 4. Finally, the last augmenting path is the path SBAT that has transit time 5 and residual capacity 1. Okay, so please notice here that we are not allowed to send flow in the reverse direction of the arc AB or reversing time. So when sending flow along this arc, we have to make sure that there is some flow coming out in the opposite direction so that the two flow cancel out. So I know that this sounds very abstract, so I'm going to show you with an example how does an Ellis-Rava flow looks like. So I'm going to show you a sequence of snapshot. So at first, we send flow along all the paths. And after 1 unit of time, we stop sending flow along the path before. Here I'm using as a time horizon 6. After 2 units of time, we stop sending flow along the paths P2 and P3. Notice also that at this point, so after 2 units of time, we stop sending flow along the path AB. So this corresponds to the situation explained earlier when the two flows, so the flow coming out of P1 and P4 cancel out, so when they meet. And this goes on for 1 unit of time. Then we resume sending flow along AB. And finally, please notice that the last particle that arrives at the sink comes from all the 3 paths. So our algorithm for the setting with scheduling cost function is very similar. This is also based on the successive shortest path algorithm for the static mean cost flow. But here, rather than a time horizon T, we have a cost horizon C. So in each iteration, we compute the shortest augmenting path, and we send flow along this path in an interval chosen maximally so that every particle that arrives from this path pays no more than C. So for example, if we consider strictly unimodal scheduling cost function, we have that the first and the last particle that comes from a path has exactly cost C, and all the other particles have a smaller cost. Now also notice that in the case of strictly unimodal scheduling cost function, you have that if we increase C, we also increase the length of this interval, which means that we also increase the total mass of flow that we send. So given a total mass as an input, we can compute C with the bisection search or with the Megiddo's parametric search. So as I said earlier, this flow generalizes the Ellis-Rava flow. In fact, if we are given this raw function, this scheduling cost function as input, we have that the optimal flow over time with scheduling cost is exactly an Ellis-Rava flow. So in this scheduling cost function, we have that the penalty, so the scheduling cost reduces with rate alpha, where alpha is the per time cost of travel time. And it becomes infinitive after this star.
Dario, here's a question in the chat. Whether there are some assumptions on the cost function. Does it have to be monotone or something?
So no, we can prove it with any general cost function. Mm-hmm. So now I'm just explaining the situation for a strictly unimodal scheduling cost function because it's easier to understand. But if we drop the assumption that so basically, you can prove it that the algorithm extends to any general cost function. We just have to change few details for that.
Thanks.
So the LSR flow has the strong property that says that simultaneously for any time horizon t prime, we have that the amount of flow that arrives at the sink before time t prime is the maximum as possible. And the proof that show that the flow is an LSR flow show this strong property. An analog property in our setting would be the one that says that simultaneously for any cost horizon C prime, the amount of flow consisting of agent that pay at most C prime is the largest possible. But unfortunately, this is not true. This does not hold. We have a countersample for that. And this implies that we have to use a different approach to prove the optimality of our flow. And we prove it with duality. In fact, this problem can be modeled with a double infinite linear program. So with the linear program that has an infinite number of variables and an infinite number of constraints. And the situation is subtle with the infinite linear program because we might have that both weak and strong duality fail. But in this case, they hold. So in this case, strong duality hold, and we prove it. So here are the dual variables. So we call them pi v of theta for any node v and any theta, and mu e of theta for any arc e and any time theta. So we first give a certificate of optimality, and we show that if the primal and dual variables satisfy this condition, then they are both optimal. So then we have strong duality. And these conditions basically are complementary slackness condition. Then moreover, we actually give an explicit description of the dual variables. So basically we can compute the dual variable without having to solve the dual P. And this description is based on the same successive shortest path used in the algorithm. And also to show that these dual variables satisfy this condition, we have to investigate some structural properties of the residual graphs. So now I'm going to focus on the game theoretic setting. So we know that in an equilibrium, we have that all the agents have the same cost and none of them can reduce its cost. And usually we have that equilibrium do not describe optimal flow. They are quite inefficient. And one way to improve the equilibrium behavior is to introduce extra cost on the arcs, so to introduce tolls. And this also might make the agent change the route, or they might force them to chase a different departing time. So to improve the equilibrium behavior, we need flexible tolls. So we need tolls that change over time, because if the tolls are fixed, then the equilibrium behavior is still very inefficient. So now we have that the cost of an agent is given by the journey cost. So alpha times its travel time cost, is travel time, plus the scheduling cost that depends on the time when he arrives at the sink, plus the sum of all the tolls that he encounters along the way. And our goal is to find optimal tolls that are tolls for which the optimal flow over time with scheduling cost is an equilibrium. So here I can show you an example of what the optimal tolls look like. And in this example, I will use the same instance I used earlier for the earliest arrival flow. So here we have that tolls increase linearly over time, first on the arc SA. Then we will have no tolls. Then we will have tolls increasing on AT. Then we will have tolls increasing simultaneously on AB and BT. And then finally on UBT. I'm not going to show you why these tolls are optimal, so I'm not going to details, but my point is that the sign tolls is not very intuitive. but it becomes immediate with the dual variables. So now we have explicit formula for the tolls, and this is very convenient. So we found optimal tolls, but so there is a problem. We know that now the optimal flow over time with scheduling cost is in equilibrium, but it's not true that all the equilibria are optimal flow. So we might have equilibria with these tolls that are not optimal. And here I can show you an example. So here we have a very simple network where there are two arcs AT, one with capacity 2 and transit time 1, one with capacity 1 and transit time 0. So suppose that now we have two agents at A at some point. So the optimal solution, the optimal flow was to send one agent on the top link and one agent on the bottom link. And to make this flow an optimal, an equilibrium, we need to insert a toll on the bottom arc so that these two agents have the same cost and none of them has an incentive to change strategy. But now we have that we get an equilibrium even if both of them take the top arc, because again, there is no difference in cost between these two arcs, and this is not an optimal equilibrium. So even with optimal tolls, we might have inefficiency. So one solution to that would be to split the top arc into two arcs and to toll one of them so that no one will ever take this arc, and so that every equilibrium are optimal flow. And this is kind of correspond to only tolling one lane of the road. So you can imagine a road with a fast and a slow lane, which might be doable in practice. But unfortunately, there are instances where the number of lanes per arc might be very big, and this might be unrealistic to apply in practice. So we do know that flexible tolls, that tolls that vary over time are not flexible enough. But on the other hand, we have that lane tolling is too flexible. So as an open question, would be interesting to find a tolling scheme that makes sure that every equilibria is an optimal flow over time, and that this tolling scheme will be also be practicable, doable in practice. Okay, so finally, to conclude, as I mentioned before, our results extend to general scheduling cost function, and only minor changes are applied, are needed. And for further research direction, it would be interesting to use this setting, so the setting with scheduling cost, to study equilibria where agents have to choose both the departing time and the route. And we think that this might be interesting because in the setting where the flow there is a constant rate, we have that the first agent encounters no queue, so has a very small cost, while the last agent that is released encounters a lot of congestion, and there's usually a huge cost, and this is very unfair. So that will be all. Thank you very much for your attention.
Thank you, Dario, for the nice talk. Are there any questions? We have time for questions. I think there's a long lunch break. I shouldn't have mentioned lunch. I don't see any questions. I have a small question.
There's a raised hand, Britta.
There's a question?
There's a raised hand.
Joseph Part, yes. Please go ahead.
Yeah, thanks for the great talk.
Thank you.
So in this last future research part,
Yes.
So if the scheduling cost is also periodic and the agents have to choose their paths, as you mentioned, do you think that the paths they choose will also form some periodic equilibrium over time? I don't know if this makes sense. I mean, a lot of flow problems have, or at least max flow has this periodic structure.
So the paths that they choose are always the one of the successive shortest path algorithm for the starting mean cost flow.
Okay. Okay.
So they're always the same. The only difference is now you have different intervals. So in the example that I show, you have one big interval. So to each path is associated only one interval. With different scheduling cost function, you might have that you have a family of interval.
I see. I see.
Okay. So
Okay.
there's a further question by Haripriya Pulyasari. The question is, can this be applied in the multi-commodity setting?
The setting, yes, but the algorithm, I'm not sure.
Mark says yes. Mark, do you want to unmute yourself? Or I should unmute you, right?
I think he might be able to unmute himself.
Mark, can you unmute yourself?
Oh, the yes was referring to the earlier question if we can hear him.
Okay. Sorry, Mark. Okay. Okay. Sorry for that. Are there any further questions? And Dario, I have a question. So your model and your results work for time-dependent cost functions. Do they also work for time-dependent travel cost functions?
No. What do you mean by travel cost function?
I mean, it could be that maybe at rush hours travel time is more costly or something like this. And do you think it would be a problem to extend your model and results to cope with time-varying cost functions, travel cost functions?
I didn't think about that, so I don't know, honestly.
Okay,
But
so
it might be possible, more complicated, but possible.
and there's a further question. Cedrico asked, what is the intuition behind strong weak duality holding for this infinite LP?
Where are the conditions? I lost them. So like, for example, I'm not sure I understand the question. So for example, this condition says that if we have an arc where we can send flow, so if like an arc is present on the residual graph of our flow, by sending flow along this arc, we can only reduce the total cost.
Okay.
Not sure if that answers the question.
Yeah, and Neil, do you want to unmute yourself? And
Yeah, I mean, I'm just saying I would not have any good intuition for when duality holds for infinite LPs, except I guess, you know, if it's a nice situation, you would expect nice things to happen. And I guess, I don't know, it's sort of it's modeling something pretty concrete. So I guess it's plausible that this is a nice setting. But yeah, I don't know enough about infinite LPs to know quite why you should expect it to work otherwise.
Okay, and here's another question. To obtain a price of anarchy result for this model, would one have to define a time-varying lambda with smoothness? Is that the obstacle? Asked by Vasilios Livanos.
To get, can you repeat the question, please?
Sure. So to obtain a price of anarchy result for this model, would one have to define a time-varying lambda mu smoothness?
I don't think so. So for a price anarchy result, you just need the total cost of an equilibrium and the total cost of the optimal flow. And at least for the optimal flow, we can compute that cost.
I mean, maybe say, yeah, I mean, I think the answer I would say is the situation with the price of anarchy is, it seems pretty different to what happens in the static case. And so like none of the sort of schemes, I mean, yeah, we have very little idea. I mean, like for fixed departure rates, I mean, there are some negative results and then some open questions. And yeah, I mean, there doesn't seem to be an easy way to try to apply any of these static results to this model. It seems quite different in some respects.
Okay. So there are no further questions. So I would suggest I unmute all of you and let's thank Dario as well as Zara and Nico for this nice session.